but slide doesn't run. Okay, where here? So this is here just for motivation. So always very important to know the fracture toughness of pipes, because we want to stop if it's happened accident that of course certain section can be replaced, but in this thing we need to have possibility, material should have possibility to stop crack propagation. So in order to find these values, it is necessary to find the fracture toughness. You know that pipelines is already explode will open on this way because you have the 2 times higher stress in hook stress than in perpendicular direction, and this is the reason why it's happened. And here is the result from the test in one laboratory. It was happening actually more 15 years ago. So motivation. Many scientists try to find a different way how to measure the fracture toughness of the pipes materials. Here is one testing machine from MES, from a group of Professor Previnaj and Julien Capel. And here is also a suggestion by Professor Luka from Brno, and maybe a discussion designed such a setup for the testing like CT specimen. But of course, here we want to make this test cheaper, easier, faster, and in this order, it's easier to make the ring and the test of the ring. Also, you have a possibility to test very small specimens. That was done in Ecodemy in France. They use the same procedure, and so we actually find the correct fracture toughness value. So of course, in order to find the fracture toughness and to select a proper material, usually you have the standard test procedure like ISTM 1820 for 3-point bend or CT specimens, the toughness. But also we need to compare with the values of stress-strain behavior, what we did. Here we will try to find the stress behavior via RMS. So we will measure the displacement and try to find the displacement of the surface, directly compare with the cell value. In order to avoid residual stresses and to have the real materials, because the pipes, you notice the form, and this material is not the same, it should have involved material. And this was the program for my PhD student, that we use the spark rolling and then make this group of standard specimens with different orientation of the notch from the surface, the long surface, respect the rolling direction, and also CT specimens group, and also the small, bigger, and 3-point bending. But also we made the set of pipe rings, which was in different position, and made from these specimens actually want to compare the toughness on both groups. So here is so it is how to measure. It is one way that we try to compare the 3-point bending with the same notch, and then made a fatigue pre-crack, and also have a specimen for bending testing respect to this real line, and we have the support, the bending, and perform those type of tests. So here is the results of tensile test, which was cut out from this plate. So you also have some scatter. This is the new models of elasticity, yield stress, and ultimate tensile strength. It is vary for 30 megapascals. So this is what we get, and this material has the leader's plateau. It's all used from this power testing. So the testing of setup for bending of the pipe ring is here. From one side, we have this clip gauge for correctly opening displacement measurement, and from this side, one side we measure with the RMS, so we measure displacement on the surface. We use here the Delta 5 method. It is a method proposed by Professor Schwalbe in the GKSS Research Center, and now it's called different institute. And you can see that when you perform the test, it is the specimens which they have with fatigue recrack. After the fatigue recrack, we recorded with the heat tinting. This is the reason why we have such nice blue colors from the heat tinting of specimen after the fatigue recrack. And then here is this propagation, what was happened during the sustained increasing the load. So here you can see that you have three range. Actually, first is the linear part, and then you have a small yielding range, and then you have the large scale yielding on the specimen when achieve the maximum bend force. So this here we have the three different geometry of specimens. So with the radii of 60 or 6 and 40, and also with the different crack initial fatigue crack. So this is what happened with in this case, but also we have here another specimens which was made from in respect to different direction. And you see here that is the results with crack, actually with fatigue crack and then stable crack. If you have the shorter the crack, then you get more smooth line. You have only linear part and you have the large scale yielding. Here is the for notch specimen which we perform. So it is without fatigue crack. You can see that we have the blunting line here and small, let's say, stable crack propagation, which is very similar to standard specimen where we have the fatigue crack. So in such cases, you can get comparable results, but always is the problem to find for fracture toughness the crack initiation. And here, how we found by observing the surface, and in the surface we made a lot of parallel lines, and we look between the two stages. Here is stage 353 and 354, when you have the drop of displacement, because in the moment when the crack in the inside materials start to propagate after the blunting, then you have some kind of relaxation that is like a crack closure effect. But it is actually the crack in the middle start and make the tunneling, but on surface you will have no crack propagation, but you have relaxation because materials are able to relax to go to closer. So this is happened between these two stages, and because we know the force in this stage, then we know the time and force where the crack started. So this is important to know for making the blunting line. Also here we have for CTOD value, where this happened, we make the couple of this line, which is like parallel. Each of this line has own curve, and you can see that between this 0.36 to 0.58 millimeters, actually we have some deviation, and also here the different extension corresponding to distance from the crack tip. So if you're close to crack tip, you will have a shorter. If you're far from crack tip, you will have the longer displacement of the surface. And actually, we want to find CTOD delta 5 because this can be used like direct measure fracture toughness of material. Because you didn't know which one is relevant, Then we make by RMS more lines in order to find the position after the refractography analysis, where is the crack tip moment, and then select which curve belongs to this delta 5 relevant value. So now we have two techniques. One is the determination of crack initiation, and another one is measurement of fracture toughness directly by delta 5. So here is the test results which we did on the 3-point bending specimen according to the standard. Also, we use here the same techniques for cores. Of course, you can use also for displacement measurement in delta 5 too. And this is now our results for this 3-point bending specimens is here. And we have the red is the pipering specimens with the fatigue pre-crack here. And also we have the specimens with the notch. And this is 3 in green line. And here is the crack initiation, which was determined like delta 5 here. And here is the last, when we stopped with the test. So the values when we finish with the RMS measurement of crack tip opening. So this is now we made these 3 lines. So one can say that all these results, here you have the blunting line, and you have 0.2 offset of blunting line, and value which is relevant for fracture toughness measurement here, like C2D form of C2D parameter is actually this. There is a intersection between curve, it is C2D-R curves, and this blunting line is about 1 millimeter. And here is the minimum is about this range for initiation, it's about 0.75 millimeters for this material. But here we talk that it's initiation for standard specimen is in this range, and this is here is the range of crack initiation for pipering. So we have actually get higher toughness on the pipeline or the pipering specimen than in from same material and standard approach. But what is the reason? The reason is triaxiality. Actually, is different in the case of 3-point bending specimen and also in the case of pipering specimen. So we have that effect of various deviation should be clarified by additional analysis for several different ratios of ring size with analysis of stress triaxiality, the influence of the crack blunting between standard specimen and rings, and as well different stress states. And the material in the case of ring with notch or crack, and comparison between rings and standard specimen indicates for certain amount difference of initiation and crack blunting, what you see in the previous diagram. While the overlying standard curves and curves from both ring types are similar in the range of standard crack growth. So the finding for this study underscore the potential of pipering notch bend specimen as alternative to standard specimen for fracture toughness testing of in-order pipes lines. The observation of similarities and C2D curves, particularly in the stable crack growth region, validate the reliability of this piping specimen capturing essential fracture behavior. The piping notch bending specimen demonstrates promising applicability for practical fracture toughness evaluation in scenarios where standard specimen preparation is unpractical or impossible. And it is actually, I hope, that future will one step make forward to standardization of piping toughness measurement on this specimen. So thank you very much for your attention.